Alright, so let's talk about organic chemistry. So organic chemistry studies compounds containing carbon, but not all the carbons, very specific carbon. It is what's called an organic carbon. Organic carbons form bonds that at the end of the day are arranged in the tetrahedral shape right here. So we're going to learn about organic formulas. Molecular formulas, like these ones in structural, we include all bonds, including numbers of atoms, arrangement of bonds, this is the full structural form. In condensed structural form, we do not show the bonds between the carbons and hydrogens. We only show bonds between the carbons and between the carbons and functional groups. So functional groups are the parts of the organic compounds that determine the chemical properties of these compounds. So there are different functional groups. We can refer to the back cover as they suggest. So here are some functional groups. Double bond, triple bond, methyl functional group, hydroxyl functional group, thiol functional group, ether, aldehyde, ketone, carboxylic acid, ester, amine, or amide. You don't need to memorize all of it. I just want to show the variety of functional groups in the organic compounds. Now, naming organic compounds is pretty complicated. We're going to try to do some basic naming. Okay. So, stem name or prefix is based on the number of carbons in the longest chain. So, for instance, 1 carbon is meth, 2 carbons is eth, 3 prop, 4 bute, 5 pent, hex, hept, oct, non, dec, and so on and so forth. And then we have very basic alkanes and is ane. So methane, butane, alkenes and in ene, pentene, octene, alkynes and in yne. So heptine, propine, decine, and so on and so forth. So in our first experiment, we will be working with the model kits like this. And our very first task, so black are going to be the carbons. You can see there they have 4 openings, 4 bonds. Each hole represents the bond. So if you look at this, we have 2 holes here and we have 2 holes here. So total 4, which means 1 carbon can form 4 bonds. Now I'm going to place the bonds into each hole. Okay. And now, so you see tetrahedral arrangement. Now I'm going to place hydrogen at the end of each bond. So molecular formula of this compound, quite obviously, is CH4. And the structural formula of this compound will be like this. So CH4. The name of the compound, there are no double bonds, so it's an alkane. 1 carbon means that we just got methane. Now we're going to remove 1 hydrogen atom and put a carbon in its place. Okay. Now on this carbon we're going to put more bonds into the empty holes. And we're going to add more hydrogens here. So now take a look. C2H6. And the structural formula of this compound can be drawn as this is the molecule of ethane. Now we're going to add 2 more carbons. And then we're going to add enough hydrogens to fill up all the spots. Okay. So you can count it yourself. This is going to be C4H10, the molecular formula. And the structural formula, I leave it largely to you. But so what you need to do, you need to draw 4 carbons and then connect each carbon with hydrogen and so on and so forth. Now, here's what we're going to do. So we're going to remove one of the hydrogens here. And we're going to place carbon right here. So now you see that this molecule here, it has the same number of carbons, 4. It has the same number of hydrogens as compound A10. But so the molecular formula of the compound B will be the same as the molecular formula for compound A. But the structural formula is going to be different. Take a look. Okay, so 3 hydrogens here, 3 hydrogens here, 3 hydrogens here, and 1 hydrogen here. So this is your compound A with the molecular formula C4H10, and this is your compound B with the molecular formula C4H10. Same molecular formula. So structure is different, but molecular formula is the same. This property of organic compounds is called isomerism. Isomers are compounds that have the same molecular formula but different structural formulas. Isomerism is existence of two or more isomers. So for instance, isomers will have different names. In this case, this compound is a butane. This compound is 2-methylpropane. 2-methylpentane and 3-methylpentane are isomers, but they have different structural formulas. So the site of attachment for the group, like methyl group, makes a difference in the chemical properties. So the main chain, is numbered from the end that is nearest to that little side chain. Now we're going to play with not isomers. So what we're going to do, we're going to build a chain. We're going to get rid of all the hydrogens here. And we're going to build a chain with 6 carbons. Okay, so you can see that this chain can rotate like this, like this, like this, all kinds of shapes. Okay, so this ability of the bond to rotate allows a typical hydrocarbon to assume various shapes depending on the length of the chain. These are not isomers, but the environment that is watery, such as in the cell, the chain will make the shape that is the smallest possible. Now let's talk about geometric isomers. So we're going to build a 4-carbon chain with a double bond between these two. For this, I specifically use this elastic. Connections. Let's see if I can fix it actually. Okay, so that worked. Okay, so chain bends at the double bond. This is the compound C. Now, what I'm going to do, I'm going to change the arrangement of the double bond, and now I'm going to have a compound D. So you can see that compound C and compound D have same molecular formulas, but structural formulas are going to be different. So how different they are going to be. For compound C, I had this formula essentially. For compound D that you can see on the screen right now, the formula was this. This is called trans isomer and this is called cis isomer. So this compound C and D cannot be twisted one into another without breaking bonds. So I had to break the bond. Okay, you see that? I had to break the bond. Now this is called geometric isomerism. So, as I mentioned, one is the cis isomer and another one is the trans isomer.